guys, hope all of us are doing fine. My name is Ernest, and I'd like to welcome each and every one of us to my channel of Ernest Sciences and Mathematics TV channel. In today's discussion, we're going to look at one of the conditions that we have to consider in order to find the maximum probability of a particle being found within a one-dimension space or a one-dimension box, as we had looked at in our last discussion. Therefore, our discussion is going to be a concept of a particle in a box, of course, which is going to be considered under normalization condition. And from our last discussion on the concept of a particle in a box, we had given a general equation using this wave function that represents, of course, this specific particle in a one-dimension box. And we had said that we can represent this one using n pi x over L, whereby we mentioned that this particular aspect of L is the distance between these two boundaries for the x is equivalent to 0 and x equivalent to L, implying that L is the distance between this separation distance between these two walls, and the two walls are going to be given as infinite walls as such, and the outside space is going to be a restricted area where the potential of that specific region is infinite. So in this case, I had argued that from our first discussion, we can be able to give this specific general illustration for the equation, and therefore for us to find the value of this unknown aspect of A, we had said that A is basically an unknown constant, and therefore the concept of a normalization condition is going to assist us find this specific aspect over A, or this unknown constant over A, of course, which is of course going to assist us in describing the probability of finding an electron in a one-dimension box. Now, for this to be achievable, we're going to say that the probability of finding this electron within the region of 0 and L, perhaps I can just divide this one. 0 and L can be given as from the bonds, Max Bonds argument. We're going to create this condition whereby this specific function is equivalent, or the integral of this specific function in a one-dimension box over x is equivalent to unity, and of course that is going to describe the maximum probability of finding this electron. Now, therefore, we're going to do a substitution for this specific function, and therefore have a function of this specific probability given in terms of the integral between 0 and L is given as the square of this particular unknown constant A, and then we're going to have the sine over this, or the square of the sine of this specific function given as n pi x over L, and therefore we're going to consider this particular probability, and the total integral for the maximum probability is going to be given as 1, as I've mentioned. So therefore we're going to do an integral of this specific equation. Now, from integration of trigonometric functions, we said we're going to take this specific constant out, and then we're going to have this given as the integral of f 1, or rather 1 minus the cosine of this specific function. So we're going to have this one given as 2n pi x over L, and then this one is going to be given in terms of so the range between these specific integrals we had said is between 0 and L. So basically, whatever that is inside this square brackets is going to represent the square of the sine over n pi x over L, which is basically from the laws of integrals for trigonometric functions going to translate into this. Of course, we're not going to go into deeper mathematical aspect of this, but just have this representation given as dx is equivalent to 1 given as such. So we're going to take this particular constant out, of course, which is going to combine with this particular aspect of A. So therefore we're going to have the square of A over 2. So we have taken this one out, and then we're going to do an integral of those specific aspects in the brackets and have it as x. So integrating with respect to x, this is going to be x, and then the integral of the cosine of this function is going to give us a negative, which is minus the sine over this specific function that we have given into 2n pi x over L, and then we're going to have that one divided by, so the whole of this is going to be divided by 2n pi, well, just 2n pi over L given as such, and then we're going to have this one within the limits of 0 and L given as such. So basically this is going to be a function of this equation whereby we are trying to evaluate the integral of that specific function, and this is going to be equivalent, so perhaps I may do away with this section, and this is going to be equivalent to 1 given, or a unit given as such. And of course further evaluation is going to give us 2 which is going to be, or 2 which is going to be given in terms of L minus 0, and this is going to be 0 minus 0. So this basically the substitution of these values of 0 and L in this specific equation, and this is going to be given as a unit as such. So basically the value for L is described as 2 over L given as such, and this is going to be the value of this known constant, which is the root over 2 over L, where L, as I had said, is going to be the distance between that one. So it can be given in various versions of perhaps XA, but in our case here we're going to use the value of L. And in this case, of course, giving a normalization version of this specific condition is going to assist us come up with the value of this unknown A that we have described. And in trying to create a version of this equation that has the value of the evaluated value of this specific A, then we're going to have the wave function for this particle in a one-dimension box given in terms of A is equivalent to L. So A is equivalent to the root over 2 over L, the sine over n pi x over L. So normalizing this specific condition, then therefore is going to assist us come up with an evaluation of this unknown constant A that I've given above, and this is going to be the final equation that we're going to come up with considering this normalized condition for the particle in a box in this specific case. Now this particular function is going to be relevant for us in trying to find the eigenvalues and eigenfunctions, which of course are going to represent the energy levels in our specific case, and we're going to consider some aspects and therefore find perhaps the numerical values of those specific energies of various levels. So catch us in our next video as we're going to look at a next discussion on the concept of finding eigenvalues or the permitted energies of these specific levels as we go ahead. So that is it for now. Kindly subscribe and engage us in the comment section, and also check the description boxes of various videos that we do. I normally put a link there which is going to consist of a similar content. So that is it for now, guys. Bye, God bless you. Catch us in our next video.